Hello there, and welcome to this lecture about monitoring vegetation. My name is Michael Runstrom. I work at Lund University and I am a teacher in geoinformatics and remote sensing techniques. When we observe the Earth, maybe one of the most important things we want to study is the vegetation, how vegetation patterns evolve. If we are losing vegetation or increasing vegetation, because this is related to the carbon balance. So the more vegetation we have, the more carbon is sequestrated in the terrestrial environments of the Earth. And therefore, vegetation monitoring is a very important topic in Earth observation. We will also talk about vegetation indices and also vegetation phenology in this lecture. Here we see this vegetation spectral reflectance curve, how vegetation looks like spectrally when we look at it from, for instance, a satellite sensor or an aerial photograph or something. We see a very typical vegetation pattern here in green. This is how the normal vegetation would look like. If it's a healthy vegetation that is photosynthesizing, we see these chlorophyll absorption parts in the blue part of the electromagnetic spectrum and also the red. So the radiation that comes in are being absorbed in these wavelengths and used in the photosynthesis process by the plant. And then it doesn't really need the near-infrared radiation as much. It reflects about 50% of the near-infrared parts of the electromagnetic spectrum. And this is due to the spongy mesophils in the leaves. And then further at longer wavelengths, we see these water absorption parts that is also typical. So this is how vegetation would look like this, the multispectral signature for vegetation. And we have the visible part here, near infrared part here, and also the short infrared part of the spectrum. So this is how we can recognize if there is active vegetation on the ground from the satellite sensor. We can see here that some of the radiation will be absorbed and some will be reflected from a leaf. So the blue wavelengths are being absorbed and not so much reflected. In the green parts of the spectrum, more of the energy is reflected by the leaves, and the red parts of the spectrum is also absorbed, so not so much radiation is reflected out. And this difference we will use when we try to classify a pixel in a satellite scene, for instance, to see if it is vegetation, active vegetation or not. The near-infrared parts of the spectrum, as we said in the earlier slide, is mostly reflected. It penetrates through the leaf down to the spongy layer of the leaf, and there some are actually transmitted through the leaf and some are reflected up back towards the sky, and then we measure that radiation. So we have different parts in the leaf. The palisade, where the chlorophyll is located, they will actually absorb the blue and red light for the photosynthesis process. The spongy mesophyll is irregular shaped cells and space, and near infrared light is either reflected or transmitted in this part. And the lower epidermis of the leaf then contains the stomata and guard the cells to control the access of CO2 and water. By looking at the spectral curve for vegetation, we can see that it's different between different species. So we can actually separate different species by looking at the difference in the spectral signature of vegetation. We see here, for instance, grape, almond, and walnut, and how they differ in the spectral signature for vegetation. And that means that we can use that difference to classify if the pixel actually contains vegetation of grape or if it contains vegetation of almond or walnut. So we see, however, that walnut and almond are quite similar. They look almost the same, but the grape is have another type of spectral signature, and we can use that then to separate different species of vegetation. We can also look at if the vegetation is healthy or unhealthy. If it's, for instance, a drought period, we would see that in the spectral signature of vegetation. So here we have two different species. I don't even see what it is, but one is healthy, the blue one is healthy, and the green one is then not so healthy anymore. Maybe it's a disease or something. And we see also the same pattern for the cluster beans. So we can actually see from space if a vegetation type is healthy and growing well, or if it's unhealthy and maybe has a disease or is affected by drought or something like that. We can also look at the signature and differentiate between the density of the canopy or the vegetation. How dense is the vegetation? How many leaves are there? And one way of measuring that is something called leaf area index. Leaf, which is then leaf area per unit ground area, which is then translated into vegetation density. And the higher leaf area index, the denser the vegetation is. And we see in the graph here that if we have a high leaf area index, we get very, very high reflectance in the near infrared part of the spectrum compared to a not so dense vegetation type then. So leaf area index is a value that we can use to express the density of a vegetation canopy, for instance. How many leaves, layers of leaf we have. And what we use mostly is the red edge shift, the difference between the absorption in the red part of the spectrum and the reflectance in the near infrared part of the spectrum. And it goes by just after the red wavelength. The curve will increase here, and more of the radiation will be reflected. So we have a strong absorption in the red here, and then we have a weak absorption and more reflectance in the near infrared because of the pattern of the spectral signature. And this is what we can use when we try to classify different vegetation types to see if a vegetation is healthy or unhealthy and so on. We can estimate biological production from satellite sensors by maybe constructing a vegetation index. But this is then the formula for the normalized difference vegetation index. And we see the formula for that measures the reflectance in the near infrared, and it subtracts the red part, and then it normalizes the difference between the reflectances in the near infrared and red. And that gives us a value of that will estimate some biological production, or actually photosynthetic activity, because we know that from the sun we get the photosynthetic active radiation coming down, and which is then the visible part of the spectrum, and then some is absorbed to drive the photosynthesis, and that's the absorbed amount of photosynthetic active radiation, and some is actually reflected up towards the satellite sensor. And if we measure the difference between the incoming and reflected, we can actually get the absorbed part, how much has actually been used by the plant in the photosynthesis. There's other possibilities to model gross primary production or biological production from a light use efficiency model, when we also use the APAR, the amount of APAR, and we multiply it by some plant potential growth value. We will not go into that so much. We stay with the vegetation index, and we saw before the formula for the NDVI. And a vegetation index is a calculated value from measurements in the red and the near spectral bands. A vegetation index captures the photosynthetic activity by constructing a value, an index value, that is related to the red shift, and can be seen as an approximation of vegetation growth, density, leaf area index, yield, and biological production. We see, for instance, the image of Africa here, and it shows the NDVI, and we have put colors to it. So the greener it is, the higher is the vegetation index value, and the browner it is, the lower is the vegetation index value. And this pattern will be exactly what we can expect in Africa, where we have the rainforests at the equator. In Congo here we have abundant of vegetation, but up here we have the Sahel belt with big desert, and the Arabian Peninsula here. We also see very clearly the Kalahari Desert in the west, southwest of the African continent. So the vegetation index captures how much vegetation we have in every pixel. There are different vegetation indices. Even if NDVI is the most common used vegetation index in remote sensing applications, there are many other vegetation indices. For instance, the red edge chlorophyll vegetation index, which is calculated by dividing the near infrared reflectance with the red reflectance and then -1. We have the normalized difference red edge vegetation index, NDRE, which is then the near minus the red edge divided by the near plus the red edge. We have another index called the green normalized difference vegetation index, where we have the near infrared minus the green divided by the near infrared plus the green. So there are many different. We have a modified soil adjusted vegetation index, for instance, that then takes into consideration the soil and try to leave out the soil footprint of the reflected signals. We have the optimized soil adjusted vegetation index, atmospherically resistant vegetation index, enhanced vegetation index. So there are many different indices that can be used, but all of them are actually using the near infrared reflectance and some part of the visual part of the spectrum, the green or the red part of the spectrum. You can go to this website and check out different vegetation indices and see the different formulas to construct them, and it's a good way to use multispectral image data, satellite data, and get only one value for vegetation by constructing a vegetation index. It makes things simpler to work with vegetation and to monitor vegetation. However, we must understand also that vegetation is growing in a seasonal pattern, which we call vegetation phenology. This is grassland pixels in Iceland over 5 years, and we see the typical annual vegetation cycle. We have in the winter time, it's no activity in the vegetation, but then when the light starts coming and the temperature rises, the vegetation starts to grow, and it reaches some kind of peak at the middle of the summer season, or a bit later actually. And then we have a senescence phase where the vegetation is going into senescence and the leaves are getting brown. It's too cold and too little light for the plants to keep growing. So it goes into a winter idle here, and then next year it will start to grow again and reaching its peak, and then going down towards the winter idle, and then next year, the third year, it will look like this, go up and down, up and down, up and down. So this is very important to be aware of when we study vegetation from space. When in the phenology stage, or at what point in the phenology is the satellite image acquired? When was it taken? Was it taken at the peak here, or is the image taken in the winter period when we don't have no activity of the vegetation? And that is, of course, very important when we try to understand how much vegetation we have in a certain place, that we actually try to focus on the vegetation peak period when we have as much activity as possible of the vegetation. And also, of course, when we are comparing two temporal images and try to see what has happened in a change detection study of vegetation, we shouldn't, of course, compare 1 year that was acquired in the vegetation peak and then with another image that was taken late in the season, because then we would draw a wrong conclusion that vegetation has actually declined, but it's just measuring two different timestamps in the phenology. Okay, that was very quick about vegetation monitoring using remotely sensed techniques. And what can we conclude from this lecture then? We understand now that spectral signatures of vegetation provide possibilities to discriminate vegetation from other objects, from urban areas or water, by looking at the spectral signature. The spectral signature can also provide possibility to separate different vegetation species. We can maybe try to see if vegetation is healthy or unhealthy, if it's stressed vegetation. We can also maybe find an early warning system of crop failure due to disease or drought or something, and that can cause later on a famine, maybe in a country. So we would know that already ahead, that we will have problems with the harvest in this region in 2 months' time, and that would be a very great help to many people that are relying on the yield, the harvest. We saw also that the red edge shift is important and characteristic for the vegetation spectral signature, and that is used when we want to calculate a vegetation index, for instance, or calculate biomass production. We can also use time series of satellite images that will provide possibilities to study phenology and see if changes are occurring in the start of the vegetation phenology. For instance, are climate change causing the start of the vegetation phenology to be earlier or later? And when does the peak occur? Is that still the same time the same time if we compare different temporal images? So is the growing season getting longer because of climate change? We can study that by looking at the phenology and comparing the phenology between different years. And if we have a time series of a vegetation index, for instance, we can also study the trends of vegetation to see if vegetation activity is increasing or decreasing. Maybe is there a degradation in place in some areas? We can find those as hotspot areas when we create trends through a time series, when we have many different years to study and analyze. And this is what you will do in the practical assignment here. You will be using a 19-year time series to evaluate the vegetation trends and see if cultivated areas, for instance, are they increasing their yield, or are there some problems with degradation in these areas? So I hope you will enjoy the coming practical assignment here, and hope you now understand a little bit of how vegetation can be monitored from space using different techniques. Bye bye and good luck.